Thank you very much. Good afternoon, and hopefully everybody staying safe there. Okay, now we will continue with the topic on classical advanced process control techniques, right? Or I mentioned previously in my other slide on conventional advanced process, or basically we can say conventional, basic classical. In my introduction, I mentioned is classical advanced process control techniques. The one that we have studied in the last lecture was the cascade and ratio. Now we go to the next one on feed-forward controls, using what we still define as classical, because it's just a slight extension of the normal conventional process control that use the PID system we have seen before. But this is a slight extension with a combination of PID and a feed-forward model technique, as we will see next. Feedforward control on the topic of this talk. Basically, what is feedforward control? Feedforward control, basically, if you can see here clear, the feedforward controller measures the disturbance or the load directly and anticipate effect on the output. So it takes control action to eliminate the impact of the disturbance on the process output. And basically, if you see the feed forward, so what's happening is that it acts on the disturbance and eliminate the impact of the disturbance on the process output before it acts on the system. So feed forward acts beforehand in an anticipatory manner. While if you don't have feed forward and you have the normal feedback system, then you will just see the disturbance coming into the system to the process. Then once you get the measurement, then only the control take action. So it's slow. It acts after the effect in a compensatory manner. So what we're trying to do feedforward is trying to act on the system before it really affects the plant. It may affect a bit, but at least we have taken into consideration disturbance in our manipulated variable. Okay, the types of feed-forward control system, we have the feed-forward control of a heat exchanger. Objectives to keep the exit temperature of the liquid constant by manipulating the steam pressure, right? So we have the steam here, so we are taking action on the steam flow before the changes in the steam affects the temperature of the heat exchanger. We have the liquid stream being heated. This is T out. So whatever disturbance that may come, and here we can see it involves two principal disturbance: the liquid flow rate and the liquid inlet temperature inside here, the flow rate and the inlet temperature. So these two disturbance we take into consideration, we measure them, use the feedforward to act on them with the required set point of the system, and then it acts on to the manipulated variable to cater for the disturbance. So it's anticipating the disturbance, doing some rejection of the disturbance, and then adjust the steam accordingly before the disturbance affects the heat exchanger. So this is a very common, very useful system to be used in a heat exchanger feed-forward control. Is a feed-forward control of a drum boiler. You have a drum boiler here, okay, coming out, producing the steam. And what are the disturbances? There are many disturbances, but these are typical disturbance that affects this drum boiler normally. And we can see here that this feed water steam flow from the boiler can be a disturbance. Changes of steam flow from the boiler or the flow of the feed water itself can be a disturbance onto the drum boiler. So the feed forward will cater, it has to measure the disturbance, basically the steam flow, measure the disturbance of the flow of the feed water, acts on to the manipulated variable, which is the feed water itself, before it affects the system, and then hopefully the steam that comes out is not much affected by the change in feed water or by the change of its steam flow itself. It's already been taken care by the so-called feedforward model that we'll see later in our lecture here. Another one, feedforward control of the station column is involved again two principal disturbance. Okay, one can feed flow is normal to affect the whole station column. The composition of the feed flow will also affect the whole station column. So these are the main disturbances. As I said, there can be many other disturbances, but we just focus on some of the main ones, the principal ones, and consider this loop only. So feed flow and composition is taken care of, measured, has to be measured. The system has to be measured to be able to implement the feedforward control. If not, it's not possible. Then we act on to the reboiler valve, steam reboiler valve, or it acts on to the reflux system. Okay, to cater for the disturbances. This disturbance does not affect this the station column much, so we will get whatever output we like to get for the distillate and the output product from the bottoms. Okay, by measuring the disturbance, taking care into the feed controller, acting on it before it affects the whole system dramatically. Also, we can have a feed-forward control of a CSTR to maintain the constant temperature and composition within the CSTR itself, and involves again two principal disturbances: the inlet concentration, temperature. The concentration and inlet temperature can affect the whole CSTR. So we measure them, act on the feedforward control, feedforward control acts on them, and it manipulates whatever is needed using this measurement for the coolant, for the CSTR, or for the output from the CSTR itself. So these two things can be used to cater, to anticipate the disturbances, manipulate them, but with the disturbances taken into consideration. So you'll get what you like for the temperature of the system as what you have designed it for. Okay, so it's a common typical industry systems, industrial system, chemical system, and these are common control system that can be used for controlling temperature and so on, for what we have seen before. Basically, example of how to design a feed-forward controller. In this case, for stirred tank heater, we're controlling the temperature, but disturbance can come from many sources. Okay, from the inlet temperature and so on. But this is the system we're looking for. Disturbance are the TI in this case, temperature inlet, manipulating the steam into the stirred tank heater. So basically, heated by the steam line, and these are the input, and inside the inputs there are the disturbances, and these are the output. So we have to relate the disturbances to be able to implement the flow. So if you have one steady state for controller, so basically we have to get the equation in terms of the model equation for the system, but we look at the steady state only to design this feedforward. So this is the temperature accumulation, temperature coming in, temperature out, and the heat steam supplied, heat by the steam supplied. Okay, so we get in the steady state form. This is 0 given by equation 2, and in order to keep the T according to the set point, the manipulated Q should change according to this equation from here. And when it's the steady state given here, so we can get Q equals to this. So equation 3 is the design equation for the steady state feedforward. There's a steady state equation, so this is the steady state feedforward controller, and it shows how Q change in the presence of disturbance or set point changes. So we have a certain set point, whatever the disturbance comes in, this is how Q should change. So this is really a relation between the disturbance and the Q. And this you can see clearly in our diagram here, where we have the inlet, it's being measured, okay, and we have that set point equation here. So it goes into this part times by this part, and this is the controller output going to the steam manipulated variable, because it's taken care by the equation just now, given by this the equation is given by to this feed-forward control mechanism here. Okay, set point with respect to the measurement of disturbance times by this. So this is the Q that we want. If there's any disturbance that comes, whatever disturbance that come in, is measured, taken care of by into the manipulated variable, and basically rejected before it comes and affect the system here. So this is basically feed forward to make sure the temperature is not affected by the disturbance coming into the system. And if you want, we have the other type called the dynamic feed forward controller. Okay, that means that the equation that we are going to use is going to be a dynamic system, right? A dynamic equation. So this is basically improve the quality of control during the transient response. So it developed by the constantly dynamic heat balance as before, but we don't make it steady state. So it can be written as before in this form. Okay, if we want into Laplace, take the deviation variable and get it into Laplace form, and then we can get again the relationship in terms of the dynamic relationship between the cube and the variable with the set point which is fixed and the disturbance that changes in Laplace form, because dynamic. So equation 5 is basically the design equation that we are going to use, okay, for we design a dynamic feed forward controller. And this can be clearly seen, yeah. If we look into the equation here, we can this block diagram just like before, where we measure the disturbance. Okay, it goes into the comparator because we have the steady state. We have the set point times this value s plus 1. The output goes into this equation, and this is going to be controller output to cater for the vector for the dynamic situation. So this is again the feedback control mechanism, but for the dynamic situation where you add just this extra part here, and the dynamic. But this is the feedback temperature control of a dynamic step 10 heater. Okay, the dynamic form. So again, takes care of any disturbance that come into this system, right? And it is measured and acted upon, and you get the feedforward control mechanism coming to control the manipulated variable here. So this is simple. And if you see the how it's being done in terms of equation, in terms of the output, okay, what sort of output you are getting for this sort of system, we can see that, okay, we have the feed-forward system. For load step change, then the static or dynamic roughly is the same. Just quickly bring down to the set point that we want. For the set point, the dynamic one goes to the set point, and then the static one goes slightly slower to the set point step change. So these are the normal change that we have to check. Normally, as we told before, the regulatory control, disturbance change, and set point control and servo control using the feed-forward slightly faster than if you do the conventional method, of course. And so in summary, design of the feed-forward control arises from the model of the process. You need a model. We've seen before. We need to do the dynamic modeling. If you don't have the dynamic modeling, we cannot implement this feed-forward controller, because we need to relate the disturbance with the manipulated variable, or many disturbance with the manipulated variable, and also maybe set point as well if we need it. If we use this to control set point, we need a relationship between set point and disturbance to the manipulated variable. So we need a controller model. This is a classical advanced control method, but still there is a model needed. So it's a model based basically, but it's not categorized so much as a model, but it's still under classical advanced process control. slight modification to the conventional system. But sometimes people can also put this into the other category, the more advanced control strategy. But because it's not so computationally extensive, so it's still under that classical. But is it sometimes you can put in between also because it's still model based. But model based, basically classical advanced model control strategy. So the better the model, of course, the better will be the controller, definitely. Yeah, if you don't have a good model, the whole equation just now we see will not work properly, will not get a good controller, and it does not work very well. And we can see dynamic feedforward better for the set point changes. Yeah, well, in some cases it's better for the set point changes, but mainly actually the feedforward is mainly to cater for disturbance. So whether you use this dynamic or we can see here the static, in terms of disturbance performance, they're quite equal. So if you do not have a very complex system, you don't have a very complex problems, you do not have something that is very intricate to solve, we can still use the steady state to cater for many of the disturbance that come in. But whatever it is we still can use the feed-forward controller because it's just all model based. It's just solved on the computer slightly, and then it gives you the output straight to the manipulated bar. And so we have different forms of the feed-forward controller. We have the disturbance coming in, we have the set point change, the feed-forward controller. This is the feed-forward control mechanism. Okay, and if you want to add a real thing like for the valve and measuring device, then this is the real one because this one goes without the measuring device. But normally we have a measuring device to measure the disturbance. So you can add the measuring device GM. This part is the typical set point part. This is the controller part output, and this again you have final control element. This one just assuming final control element is one, but if you have a final control element transfer function, you can put the GF and go into the system and this disturbance. So this is a more comprehensive feed-forward equation that we will use in the real world because it takes care of the measuring device and the final control element together with the feed-forward control mechanism that has been shown how it was designed before. So in terms of if you analyze it further and get it out further, so you can get the process output given by the Y, the process part, manipulated variable, and the disturbance side, the disturbance section of the whole equation. So if you want the set point side for the process output, so you can get put in this form. This is what you want, the set point, and then this is a manipulated variable that relates to the set point and relates to the disturbance. This is in a general form. So we give you an example for the set tank heater, but this is in a general form of the equation that you can use when you design your feed-forward controller. And so equation 8 determines the form that the feed-forward control system should have. It also determines the two transfer functions GC and GSP, which complete the design of the control system. Okay, so this one is a bit slanting. So maybe pasted on, equation is pasted on, but basically this GC is the transfer function of the main feed-forward controller, which is given by GD over GP, and GSP is the transfer function of the set point element, which is given by 1 over G. So we have the set point element and the feed-forward main forward feed control equation in general form. If you look back at the block diagram is before, and I can't move back. Once I move back, you will lose the recording and have to redo it again. So I don't slide that we don't move back when I'm recording. We will lose my recording now. So just look back what I've shown, and you can see the equation that how we develop this equation from the basic system. And for 9 and 10, it's clear that feed-forward control cannot be a conventional feedback because it's based on the model. So it's not a PID. It's not a conventional feedback controller for the feed-forward. So that's where we have the advanced part. This is advanced control, but it's not same as the conventional. It's a different type of controller. But the loop later you will see is a mixture of both and very close to the conventional conventional process control system you have seen before. And equation 9 and 10 demonstrate that feed-forward control depends heavily on the good knowledge of the process model. Again, we need to have the process model very well defined, because you have to relate that disturbance with respect to the manipulated variable very well. If you do not have that, then you're not able to get a good feed-forward control design. So that's very important that we make sure we have that. And consider the more general feedforward control once we include measuring the sensor and final control. So if you include measuring sensor and final control element, then you can get this more comprehensive equation for Y with respect to the process, the controller, the controller and the measuring element. Sorry, final control valve, set point, and then the disturbance part, process, the measuring element, the controller, and the manipulated variable. And this will give you this design transfer equation. So it's easy and easy can be identified by the following two requirements. What are they? The disturbance reaction requirement. Okay, this is the disturbance reaction part. So the design of the GC is in this form. It's the set point tracking part, because you want the set point tracking to become 1. This one, the disturbance rejection, d minus this, you get 0. This is the set point tracking part, so this has to be equals to 1, and has to follow the GSP equals to this and GC to this to make the ideal feed-forward control mechanism that will cater for both disturbance rejection and set point tracking. Okay. And in terms of practical application, you can design the steady feed-forward controller in this form, okay, where GP equals to the KP and GD equals to the KD. Okay, this is a simple form for the steady state element. Just take the steady state element part, and for the GC and GSP, you can just convert using the steady state element for this sort of system. Well, these are something that we can easily implement without a controller, because it's just a gain. So these are the practical design using the feedforward controller. Elements GC and G can be constructed easily in the same way as proportional controller, which has only proportional gain. So you can make it like a proportional controller, which can design them in a much better way. And for the dynamic feed-forward controller, it is expected to give a better result because it's more dynamic system, but you can approximate by first order lag. Just now you can just put in terms of first order lag for GD and GP first order lag, and you get this. So you can just tune beta and alpha. This is a practical implementation. I mean, you can buy it in terms of hardware. Just need to tune the gains. If you want the real one, we implement what we've seen before, the equation, put into the computer, calculate. But if you want practical system, you can just design using this. Okay, and then controller is given by equation 11. It's called lag lead element because alpha has introduced phase lead and 1 over adds the phase lag. The lag lead element is the most commonly used in dynamic forward control. The two adjustable vectors are alpha and beta. Sorry, this will be alpha and these are the tuning one. And the lag lead elements can be bought easily and not expensive, and special purpose analog computational device can be used. So you can easily buy it on the market. Before it's just like that, it's all on the market. You can buy this sort of thing. So basically, what the advantage of the feed-forward feedback is basically the feed-forward acts before the effect of disturbance has been felt by the system. It's good for slow system with significant dead time. Does not introduce instability in the closed loop response. And in terms of disadvantage, it requires identification of all possible disturbance. Of course, you need to identify and measure. Cannot cope with unmeasured disturbance. Sensitive to process parameters and requires good knowledge of the process model. And what is the advantage of the feedback? Does not require identification measurement. Feedback, one we have seen before. Insensitive to the modeling errors. It's not important about modeling errors for feedback. It's just feedback. sensitive to parameter changes. So this is an advantage. But the problem is it waits until the effect of the disturbance has been felt by the system. So that's the problem using the feedback control system. For control actions taken, it is unsatisfactory for slow processes or with significant dead time, and it may create instability in the closed loop response. So there are the advantages of the feedforward, there are disadvantages in the feedforward, and there are advantages in feedback, there are disadvantages in the feedback. So both have got their good and their bad, but of course the best thing is to combine them so that we get the best of the both worlds. We get the effect of the feedforward that will take care of the disturbance before it comes in. At the same time, also have the effect of the feedback that is not sensitive to modeling errors and parameter changes, so it can still be robust enough to cater for different types of system using the feedback system as well. So in many cases, the best is to combine them so that we can take the advantage of both controllers, and then we can design in such a way. So what we have is a combination of the feedforward feedback system will retain the superior performance of the feedforward controller and the insensitivity of the feedback controller to uncertainties and inaccuracies. Okay, if you combine them, so basically you still have the feedforward element that will take care of disturbance coming in, measures X on the feedforward by the feedforward controller, X on the manipulated variable to cater for disturbance change. So whatever disturbance should be being cancelled out by this part of the feedforward controller before it acts on the final control element and on the process itself. Right. But at the same time, we also have, as I said, shown you before, the problem with the feedforward is that it's sensitive to uncertainties and inaccuracies and so on. Okay, and where the inaccuracies and uncertainty, it's mainly in the process itself. Okay, so if you have uncertain process or uncertainty in the model parameters and so on, so it will affect. If you just use feedforward, it may affect the output. Okay, and also you need a good model. Of course, some simple model you can get a good model, but for complicated model you may not be getting a good model. So the best is to also have the feedback system that will measure the output and acts on the controller, the feedback controller, to work on this part, the output part. So you have both, the feedforward controller mainly to reject the disturbances, and the feedback controller basically to try to bring it to the set point that we want at the same time. So it acts both. Set point tracking, you should be able to get some good set point tracking, and also you are able to also reject the disturbances that come in from the system using this combination of feedback and feedforward system. So this is where they have the advanced method. It comes under the classical advanced control method. Because why? Because the feedforward controller is not this is not a standard controller. This is based on the model that we've seen before, the set point part and the feedforward part. So it's a different type of controller. It's not PID definitely, but the feedback controller is still a PID. It can be a PI normally or PID controller. So it's a combination of the basically the conventional process control, not conventional advanced process control, and the advanced part, which is the feedforward controller. So as I said, we still identify this as a classical advanced control. Advanced control, because of the definition, it has something different from the normal feedback loop, but it's an advanced control strategy, but close to the feedback one. So it's classical part. So we call it classical advanced control strategy, and taking care of both. So it should be a very good strategy. It should be easy to implement, as I said, as long as you get a good model. And so what does it mean? It means if you can, for systems that are not so complicated, not so complex, it should be able to get a good model, and definitely that means the feed-forward part can work very well. If you combine this, even if model is slightly off, not so accurate, you still can take care of it by uh, the set point, the feedback part. So of course, the feed-forward may not be that accurate, but the feedback will take care. So at least the set point tracking will go on, will be quite good, but the disturbance part may not be good if the model itself is not so good. So that part we have to be looked into, has to be catered for this sort of thing. The other thing is that it can be implemented by basically simple methods. Okay, if we use that practical feed-forward controller, we just unit the gain. The alpha beta, you just need the gain, tune the gain, and you can implement the feedforward control. So you can implement it on analog, on hardware system without the computer part. But if you are using a very sophisticated model and the equation of the feed-forward system is more complicated, you need to have a computer system, then you have to implement it on the in the computer side. Okay, basically you can use the computer-based control, yeah, direct digital control, or you can use the whatever other uh, system that is being done using the DDC system, direct digital, or the distributed control system, but the controller are being implemented in the computer itself. So it can be both ways. But of course, before, as I said, they use the practical one, the hardware side analog, simple. The feedback can easily also get hardware, simple feedback. But if you're using the direct digital control, the new uh, types of control system, then all this will be in the computer itself and can be just uh, implemented in the computer, and the manipulated variable can be forwarded back to the system itself. Okay, so this summarize basically the feed-forward control, feedback control under the classical advanced control strategies. So hopefully these two parts on the cascade ratio and this feed-forward will cover that part, the classical advanced control method. Okay, I used the word conventional before for class, as I said, for cascade and ratio, but actually and also call it the classical advanced control method together with this one. And most of it we will cover. These are the basic ones for the classical advanced control. We have other slight changes in the date time technique, the what you call a date time compensation technique. We have a few others minimal methods that not common. I'm not covering here, but you can see in the books some of the methods not so not so popular in the real world, but these are the main one: cascade ratio, feedforward, that are most popular among the classical advanced control methods. And then next, then we will go into the more what we call modern control methods that basically totally nothing to do with the PID or the conventional control method, and the way we compute the controller is also different, and you need basically computer based. It's more computer based systems. We'll see later the GMC, and then we have the AI method. There's so many others, but it's not able to cover everything. But we will cover the next one. We'll be covering the GMC, the generic model control, and then also we will start going into the AI methods, which are the neural network and the fuzzy control method in the next few lectures. And that will cover the modern control system, modern advanced control system in our talk. So, and at the end also we'll discuss further on these things. When we have a session, we can ask questions, or what we can clarify further on whatever I've taught, and hopefully we can see what it means by having the advanced control methods. What are the improvement over the conventional method? Conventional, when I say conventional, means the PID loop. This one. When I say classical or conventional, advancement something more different from the normal conventional methods. That's what our definition before, but I have sometimes interface between classical and conventional. But if it's advanced, means it's the same thing. It's advanced control. Classical means it's conventional, similar to classical advanced control. But we just say conventional process control, then it means just the normal feedback control with the PID sort of methodology. Okay, the feedback will be tuned normally. The feedforward will be tuned using either on the computer or by the normal the standard one that you use just now. Just the gain and be used in that way. Okay, thank you very much. I'm sorry they made some disturbances, background disturbance here and there. It's from the home, so there are other factors coming in. So just ignore the noises coming in, and hopefully we can discuss further in the next lecture. Okay, and so for this equation, for the closed loop and feedback, you see similar equations. I don't go into it more in detail, but and you can see the transfer function for the feed-forward loop is given by minus the slight change in the block diagram, so it's the minus sign coming in there. But whatever this is the same thing. What you want is the manipulated variable with respect to the to the feedback side and the feed-forward side. Manipulated variable with respect to the disturbance side and the output side, the feedback output side. Okay, so slight changes here. This is still the normal characteristic equation, and you can see once you have a characteristic equation, means this sort of thing you still have to be careful because you have an instability problem. There's another issue. Once we introduce feedback, you get unstable problem, instability, and that can be checked by through this characteristic equation. But just feedforward, you don't have the feedback. Just feedforward, you don't have the characteristic equation issue. You don't have an issue with stability. That's another advantage of just using feedforward. But the minute you combine with the feedback, then you also have issue of stability issues coming into the design, and you also have to look into that. So that's why it's important just to come out with this to see the effect of this stability, and also how the tuning with respect to the feedback and the tuning also on the feedforward. But tuning for the feedforward does not affect the stability. The tuning for the feedback will affect stability based on the characteristic equation here that you have studied before. So this is the output with respect to the disturbance. Okay, and for set point changes, and for that one is given by GC 2 equals to. Okay, so that's all what we have for this class. So we hope that we can discuss further if there's any problem, any question on this topic. Okay, there's nothing. Thank you very much. So we will start with the next topic on the modern control strategies, modern advanced control strategies. Okay, starting with the GMC. Thank you very much.